Morning. Today we're going to apply transformations to the two new graphs that we've talked about, this unit, the exponential graph, and the logarithmic graph. To do that, we need to remember the basic properties of the graph. So the domain of an exponential graph, which would look like that, assuming you have a base greater than 1. But this domain and range, all these properties do apply to a graph with a base between 0 and 1. Our domain is all real numbers. Our range is 0 to infinity exclusive. There is no x-intercept. The y-intercept occurs at 0, 1. And we have a horizontal asymptote at y is equal to 0 or the x-axis. Now, as I said, here's the shape for a graph where the base is greater than 1. The only thing that's going to change is this is a decay function and you have a base greater or between 0 and 1. This graph here, this little sketch, is a logarithmic function with a base greater than 1. And here you have your logarithmic function, or the sketch of the logarithmic function, with a base between 0 and 1. Now, remember that exponential functions and logarithmic functions are inverses of each other, so we are going to interchange everything. The domain of the logarithmic function is 0 to infinity. Our range is all real values. We do have an x-intercept at 1, 0. There's no y-intercept because we have a vertical asymptote along the x-axis, or along the y-axis, x is equal to 0. Now, these are for the graphs with a have-not being transformed. Just y is equal to c to the power of x, or some value base. Now, we use b a lot of the time, but we use c here because b is going to be included within this. Now, for this function here, this is just a reminder. Now, I am going to rewrite that with 1 over a. Reminder, we know what all of these do. We spent the last 4 months working with them. We have a vertical stretch, y factor of a, in the x-axis, and we also have a vertical slip. So we are either stretching it this way or we are slipping it that way. Our b value is a horizontal stretch by a factor of 1 over b. Y-axis, and we also have a horizontal flip. Sorry for the cool board with it. So we are flipping a graph that looks like this. We could flip it to look like that. And that looks familiar to us. Those are our two exponential functions. But we do talk about the flip. We have to remember, with the way that the graphs are written and the functions are written, this b value here is inside the function, so it's horizontal, but it also has to be the reciprocal. If I write the function with the a over here and there's a number 2 with it around this bracket or outside this bracket, I still have to take the reciprocal of that number. When I write it in this manner, not so much. But we aren't doing anything different. We're just saying when we have our a next to the function, we've already dealt with the reciprocal by moving it over to this side. C is a move left or right. And D is a move up or down. Okay. And again, just like before, we need to have it written in a form where you have your horizontal stuff written in a factor and your vertical stuff written in a factor also for this to work perfectly. So we have a function, exponential function here. We can use our understanding of this graph, which we know to look like this, and we could plot in some points if we wanted. We would have 1, negative 1, 1/2, 0, 1, 1, 2, 2, 4. Now, if we wanted to plot that by using this, we can define or find our stretches and reflections. What we have here is we have the 3 outside the function. So we have a vertical stretch by a factor of 3. X-axis. So we're getting that one bigger. We have replaced the x with an x plus 4. Okay, well, that means we need to move this to the left. Our x value doesn't have to be as large to get the same y value out. So we have a move forward left and 3 down to this guy. Now we would be able to plot that quite easily using a table of values like this. Okay, it says describe, it doesn't say plot, but we could plot that if necessary. So my graph is going to look something to that effect because we moved it down. Now, we moved it down, so we now know that our horizontal asymptote is now y is equal to 3. We stretched it first. Horizontal asymptote didn't change because it's on the y, or because it's y is equal to 0, the x-axis. We moved it left, doesn't change the horizontal asymptote, and then we pulled the entire graph down. So now my horizontal asymptote is y is equal to 3, negative 3. Not 3, but negative 3. Okay, well, here's what we were doing. I did actually plot it. So to vertically stretch it by, here's a data table. We just plugged in some values of x and got out our y's. To vertically stretch it by a factor of 3, this becomes negative 2 3/4, negative 1 3/2, 0 3, 1 6, 2 12, and then 3 4. Then to move it 3 left, it's going to be negative 5, 4, and so forth. And then we are going to move it 3 down from that point. 3 down off of that is going to be negative 9, 2 1/4, negative 2 3/4, negative 2 1/2. What the hell? -3 and 0. Why am I bored doing that? -2, 3, -1, 9, 0, 1. And this would be -1.5. Now, we could then sketch it quite easily. As I said, we have a vertical or a horizontal asymptote here. We have a y-intercept way up there, so as I sketch there, it's going to look something like that. Now here, again, we want to sketch without technology. Let's apply what we know. I have determined these points by using my function y is equal to log base 2 of x, power of x, or power of 2 that will get me to x. So if I have 1/4, I get out -2 and so forth. What I have here is I have a horizontal stretch by 1/2. Okay, that 2. I have to take the reciprocal of it. And then I have 2 right, 1 up. Okay. Now, what I hear is I now know, with the 2 right, I now know that I'm going to have a vertical asymptote at x is equal to 2, because I've also moved the vertical asymptote to the right, 2 points. Everything else we can work with also. So vertical stretch by 1/2, I end up with 1/8, -2, 4th, -1, 1/2, 0, 1, 2, and 3/2, 8. So 2 right, this is going to be 2 and 1/8, and 1 up, going to be -1, 2 and 1/4, and 0, 2 and 1/2, and 1, 3 and 2, 4 and 3, and 5. No, I'm messing something up here. No, 2 right, so 2 right from that. What I messed up was over here. This is backwards. That should be 2 and 4. So then that would be 1 and 4. I'm just going to skip that line. Something wrong with that. I have to fix. Sorry. And then the 3 and 8 would become 3/2 would become 3.5 and 9. Something went wrong somewhere. Where did I go wrong? Base 2, 4, 2. This is what's wrong here at the bottom. 4 and 2 is correct. This is 8 and 3. That's backwards. And then this would be 4 and 3. And then we would have 6 and 4. Okay, again, stupidity on my part. I'm sorry. So we know the sketch. We can plot it. We're going to have 2 and 1/4 as my x-intercept. My graph will look like this because I've stretched it. It should be 2 and 1/4 as my x-intercept. Again, we're not doing anything we haven't already done. We're just applying it to 2 graphs from before. Have to remember The thing that's going to affect your asymptotes is in a logarithmic graph, where we pick up the graph and move it left or right, or in an exponential graph, where we pick up the graph and move it up or down. The stretches don't affect the horizontal stretch, assuming we do it in the order we've talked about: stretch, then reflect, then translate, because we're stretching around the line that the horizontal or vertical asymptote falls on. So the asymptotes are affected by the moves, depending upon which one you have: vertical in an exponential function or horizontal in a logarithmic function. Without technology, identify the following: the equation, the asymptote, the domain, the range, and the x and the y intercepts if they exist. So we can do everything with except that just by talking about transformations. We have, this is log base 10, remember? Common logs, we don't write the base 10. What we did here, we moved it 10 right, 1 up. Oh, sorry, 1 down. So the equation of the asymptote is normally in an untransformed function. X is equal to 0. So the equation of the asymptote now is x is equal to 10. That affects my domain. My domain will now become 10 to infinity, exclusive. Now, I know that because we did not do any type of reflection. We could also reflect this guy in the other direction, but we didn't in this case. The range will not affect the domain. The range of a logarithmic function is all real numbers, so moving it up or moving it down 1 will not affect the range of that function. The x and the y intercepts, we can do the x-intercept without doing actually any math. The x-intercept of an untransformed function for a logarithmic function is 1, 0. We did not stretch it, so the only thing we did was we moved it 10 to the right. So now our x-intercept is at 1, 0, or 11, 0. Okay, just because we moved it. That's what we get tired of this board. So there's our there's one way to determine the x-intercept. The other way to determine the x, or actually, sorry, I did mess that up. Okay, if it was just a transformation to the right, I wouldn't have to worry about it. But I also did move it down, so I do have to fix that. I'm sorry about that. If you only had a transformation to the right, you could do it that way. That was my mistake. So what I have to do here is I actually have to, we know that the x-intercept will be x, 0, x, and some number x and 0. So I'm going to plug it in. 0 equal to log base 10 of x minus 10 minus 1. So we have 1 equal to log base 10 of x minus 10. Okay, well, take this guy and turn, since we have an exponential equation, or sorry, a logarithmic equation where we want to solve for the unknown, I am going to write that in my exponential form. 10 to the 1 is equal to x minus 10. X is equal to 20. And that's because we dropped, we took the negative 1 down. So I tried to do it without thinking it through. There's always a way to figure out the x-intercept. Plug in 0 for y. Now, plug in 0. Is there a y-intercept? Well, in the shape of your head, you should know the graph is going to go like that. No y-intercept at all. Proof, algebraic proof that there's no y-intercept. Plug in 0 for x. Now here is where what power of 10 will get you to negative 10? There is none. There is no solution where I can go 10 to the power of something and get negative 10 out. Okay, one of the range, the domain of any logarithmic function is greater than, any logarithmic function that's a single degree. First degree is greater than 0. So we can't figure out log base 10 of negative 10. So there is no y-intercept, as we can see by this quick little sketch that we did. Okay. Now, this one here, we want to go ahead and say, okay, we have a horizontal stretch by 2 and a move 6 left. We would be wrong. Okay? We do not have the ability to get the proper horizontal move in this case until we write it in our factors form. Okay? Again, what's happened with that, to get this graph, we've done the stretches by horizontally stretching and then moving a 6. But we always want to do the stretches first. We always want to have it in this factors form. So we got the horizontal stretch correct, but we want our ending up moving it 3 to the left. Okay? So we have the equations of our asymptote. That's easy. The stretch does not affect the asymptote. The horizontal stretch, we have a vertical asymptote, but the vertical asymptote is x is equal to 0. So if we stretch x is equal to 0, we end up with x is equal to 0. So the only thing that we have is our move 3 to the right. So our horizontal asymptote now becomes x is equal to negative 3. So my graph will look with my asymptote over here. That affects my domain. My domain was 0 to infinity. I stretch it, well, now it's still 0 to infinity, and I move it 3 to the left. Now it's negative 3 to infinity. The range, we didn't do anything to the range. It's going to stay the same. We are going to have an x-intercept and a y-intercept. The x-intercept can be dealt with by transformations. We have 0, 1, that becomes 0, 1/2, because we horizontally stretched it by a factor of 1/2, and then we move it 3 to the right, it becomes 0, negative 2.5. So our x-intercept is negative 0 and negative 2.5. Now, we can also do that by plugging in 0 in for y. What we were talking about, 2. And so we turn this into our exponential form, 2 to the 0. The log is equal to 2 x plus 3. 2 to the 0 is 1. Divide both sides by 2. And we have our negative 2.5. So again, whichever method you want to use to figure out your x-intercept. My y-intercept can be dealt with in a similar way. We know the y-intercept is going to have an x-coordinate of 0 and some y-coordinate. So plugging in 0 every place you see an x, log base 2 of 6. And that would be your exact value, exact answer for that. You could then use your calculator to figure out the approximate value, but I'll just leave it as the exact value. So somewhere around 1.4-ish. Okay. Now, the next step is here's a graph. We perform some type of a transformation for this guy. Okay, and we're going to do this as basically as simple as possible. We started with y is equal, or f of x is equal to 2 to the power of x, which is this one here. We have, what have we done? Well, one thing I know we have done is we have vertically stretched this because our y-intercept has increased. So we went from a y-intercept of 0, 1 to a y-intercept of 0, 3. So we have most definitely done a vertical stretch by 3. Now that's as simple as possible for this one. We could also compare 1 and 2, and we look at it, we should be 1 and 6, which looks about where we are here. Sorry, 1 and, here's 1 and 2. So we should end up being 1 and 6, which is fairly close to what we see. So the only thing that I see that we've done here is a vertical stretch by a factor of 3. We could, if you didn't figure out that what the vertical stretch was by a factor of 3, but you knew there was a vertical stretch, y is equal to a 2 to the x, and plug in 1 and 6, or 1 and 6, which is the point that I have here, and you would find your a value is 3. I know there's no vertical move because I still have the same horizontal asymptote. Could I have performed a horizontal move on this? Possibly. But it's much easier to look at this guy, much easier to look at this guy and just go, it's a vertical stretch. It isn't a horizontal stretch because the y-intercept changed. With a horizontal stretch, you would see that guy stay the same because we would be stretching it around that line. As I said, it could be a horizontal move, so we would have to go we would have to find C in some manner, and our manner would be, we would put a 6 here, we put a 2 there, a 1, and solve for C. I don't really want to, but I can. Okay, take the log, or basically turn this into logarithmic form. 1 minus C is equal to log base 2 of 6. So C is equal to 1 minus log base 2 of 6. So you can see that there is a horizontal move that you could find. It might be much easier to figure out that there is a stretch. Now, the reason why it can look like that, we could take, what we've done is we've taken this point here and moved it over so it hits there. And this point here moves over so it hits there. But the vertical stretch is the easiest one to look at for that. Now this guy here, we have the original function, f of x equals log base 1/2 of x, which is this one here. And the reason I know that, okay, maybe I don't know that, that's wrong. This is my original one, f of x. Now, I know it is because It has a vertical asymptote of the y-axis. So what I've got here is I've got at least a move, okay? Because my horizontal asymptote has gone that direction. The other thing that I see is I've got a stretch, also a horizontal stretch. If I look at the original graph, the distance between the vertical asymptote and the x-intercept is 1. The distance from here to here is not 1. It's greater than 1. It's 3. It's 4. Okay? So we know we have a horizontal stretch, or again, the easiest way to look at this is we have a horizontal stretch. We also have to know that we have a horizontal move. The vertical asymptote moves 2 units that direction. So our function is going to be log base 1/2 of b x plus 2. And we found that by the fact that our vertical asymptote moved 2 to the left. Now we have to find b. Now you can do b by, it was initially 1. The distance between the vertical asymptote and the x-intercept was 1. The distance is now 4. So we can say that it's going to be a horizontal stretch of 4. That would mean b would be equal to 1/4. Let's see if we can make sure. We have this point 0, 2. I have no idea why I keep doing that. 0, 2. So let's plug these guys in. 2 is equal to log 1/2 b 0 plus 2. We have 1/2 the power of 2 is equal to 2b. Power, I guess, me to here is equal to 2. Okay, so I've made some type of error in my thought process. I'm not going to get no, I don't have 2b. So basically, I'm going to have 1/4 equal to 2b. b is equal to 1/8. Now, I'm not sure why what I'm doing. I know. It really does help when I don't mess up. The point that I'm plugging in here is 0, not 0, 2. Or sorry, it is 0, 2. So, no, I had done that correctly. I'm sorry, it's early in the morning. B is equal to 1/8. So our equation is y is equal to log 1/2, 1/8, x plus 2. I'm going to look at that and I'll talk to you about that during class because there's something that I'm not seeing here because it should be a horizontal stretch by a factor of 4. But what I'm seeing with my math, I get a horizontal stretch by 1/2, or by 1/8. Sorry, a horizontal stretch by 8. So I will take a look at that and I will talk to you in class. Get time, work on these whiteboard questions, and I will be going over those in class. Thank you. Have a good one.